Okay, let's do part 3 of lab 21. So we're going to see how to build up logic gates from uh, MOSFETs. Okay, so initially let's try a logic family called NMOS, which uses only N-channel FETs with a pull-up resistor. So here we have, this is an NMOS, depletion mode, no, enhancement mode. Enhancement mode, N-channel MOSFET, right, enhancement mode, N-channel MOSFET, which is pretty analogous to an NPN bipolar transistor. Here's the gate, the source, the drain. Remember, gate, drain, source from left to right. That's kind of analogous to base collector emitter, which we saw for the power, the high power BJTs. There's this 10K resistor from the drain up to +5. The source is grounded. Here's our input signal at the gate. And then this goes to, so this is scope channel 2. And this is AWG channel 1, and it's also scope channel 1. And we have, actually right now we have a square wave going in. I think, okay, yeah, that's fine. So, oh, here's how it's built. Okay, so here's my AWG channel 1. I have scope channel 1, just looking at that down here. That's going to the gate. All right, so here is the gate. Then the drain has this 10K resistor up to +5 volts, and I'm observing it with scope channel 2. Then the source has this black wire down to ground. That's it. Okay. Then let's take a look. So I have a 1 kilohertz square wave going in, and the low value is 0, the high value is +5 volts. So it's 2.5 volts amplitude, 2.5 volts offset. And I look with the scope. So yellow is the input, blue is the output. And you can see when the input is high, the output is low. When the input is low, the output is high. So it is a logical inverter. I guess I should have mentioned that. So this is an inverter. And then one thing you can see is when the output goes from low to high. See, now when this transistor is on, so in other words, when the VGS is above V threshold and the transistor is on, the output gets pulled down with a low resistance to ground. When the transistor is off, so when VGS is below threshold, the output is pulled up kind of gently through this 10K resistor. So the resistance to ground when the output is low is much smaller than the resistance to +5 when the output is high. And one interesting consequence of that is when the output switches from low to high, you can see this RC time constant. So we're at 200 microseconds per division. So here is a high to low transition of the output. Here's a low to high transition of the output. Here's another high to low transition of the output. Let me zoom in on this transition, and you can see a 1/E time of something like, let me see. It's I don't know how to use this cursor. Okay, let's see. Yeah, I don't know how to use this cursor. Okay, so this seems to go, this is like, also, what? Okay, So this seems to be, oh, I know, let's trigger on channel 1. And let's trigger on channel 1 falling. Whoops. Let me get this working. Good. Okay, so we're going to trigger on channel 1 falling, and it seems as if the time constant is something like, I don't know, let's say on the order of 20 microseconds. Yeah, it's something like 20 microseconds, right? The 1 over e time. And you could ask, does that make sense? So what capacitance? Now, we actually don't know what the capacitance is, although we saw the gate capacitance earlier was kind of on the order of a nanofarad. So let's see if we can say, yes, if we say that RC is like on the order of 20 microseconds, and we know that R equals 10 kilo ohms, so that would give us C is, we'll just get an order of magnitude number. Yeah, so I think that's plausible. If I put in RC is 20 microseconds and R is 10K, then I get C is something like 2 nanofarads. They're all kind of order of magnitude numbers, but that seems plausible since we had a gate capacitance earlier of something on the order of 1 nanofarad. Okay, but then by contrast, if we look at the other edge, then you see it looks like a very sharp transition on this scale, and we have to zoom way in. By the way, I'm not following the script, so I guess I have to look and see if I have to go back and look at the script at some point. Okay, so this looks like, I don't know, let's say that it's more like 200 nanoseconds. So that seems like 2 orders of magnitude smaller. So that would indicate that this is more like 100 ohms. Yeah, that seems not too surprising. I guess I would have thought even a little better than that, but it's a power MOSFET. Well, I don't know. Okay, anyway, it seems like we might be on the order of tens or maybe 100 ohms. Let me go look at the script now and see what we're really supposed to be doing. Okay, so actually we're doing fine. So now we're supposed to crank up the frequency of the input signal until we start to see this inverter not do its job very well anymore. So let's zoom back out to a time scale where we can see what's going on. And let's zoom out enough that we can see, whoa, oh no, whoops. That's not too bad. All right. Now, okay, let's increase the frequency. So we had a kilohertz square wave going between 0 volts and 5 volts. Let's try 10 kilohertz. And then we'll look over here at the scope. Seems like it's still doing okay. You can see, so when it goes from high to low, when the output goes from high to low, it does that quite quickly, and it's fine. But it does take a while for the output to go from low to high. And again, that's because there's some kind of capacitance at the drain, which we said is probably like a couple nanofarads. And it takes a while for that to charge up through this 10K resistor. So this is kind of marginal already at least on the, this is kind of marginal on the low to high transition of the output. We can make it definitely marginal if we go just a little bit faster. So let's go up to like 20 kilohertz. Yeah, you see now it really doesn't quite ever make it to plus 5 volts. And yeah, I think what's happening is we're effectively charging up a capacitor through that big resistance. And then I guess you could ask well, you have to go pretty fast for it to have trouble on the other side, because again, like the resistance to ground here is much smaller than this 10K pull-up resistor. By the way, I don't think I asked you to do this, but if we make that resistor a lot smaller, like here, let me replace that 10K resistor with a 1K resistor. And actually, the easiest way to do that is just to put them in parallel. Oh, whatever. Let me take a look. So we're gonna, okay, let's replace that 10K resistor with a 1K resistor, and then we'll see what this looks like. So let me do it in such a way that you can watch. All right, so the 10K resistor comes out. I'll put a 1K resistor there. And so it's going from the drain, which is the middle pin there, to plus 5 volts. And let's look at the display again. Yeah, so look at that. You see, so now it's doing just fine. So you can see that does seem to be that RC time constant, because we reduced R by a factor of 10, and that RC time constant seems to be like an order of magnitude shorter. So I think that's it for 3.1. Then let's move on to 3.2. For part 3.2, we are building a CMOS gate complementary metal oxide semiconductor. So we have a PMOS FET up here and an NMOS FET down here. So this is enhancement mode P-channel MOSFET, enhancement mode N-channel MOSFET. So this is sort of like a PNP transistor, and this is sort of like an NPN transistor. So source, gate, drain, drain, gate, source. The pinout for the 47P06 is the same as the pinout for the 50N06. It's gate, drain, source from left to right if you're looking at the print on the front. So we have a waveform generator, which is sending the same input signal to both gates. The PMOS transistor is up top. So this is actually backwards from the CMOS push-pull. Keep that in mind. So the CMOS inverter is like swapped from the CMOS push-pull. The CMOS push-pull had the NMOS on top and the PMOS on the bottom. The CMOS inverter has the PMOS on top and the NMOS on the bottom. So the output is at the drains. So if the input is high, then VGS is above V threshold for the NMOS transistor. And so this is basically on, and you get a low resistance connection from drain to source, so the output is low. So input is high, the output is low. If the input is low, then here you have VGS is below V threshold. That's what you want to turn on this PMOS FET. So then you get a low resistance between drain and source on the PMOS FET, so the output is high. So it's a low resistance connection from the output to ground if the output is low. It's a low resistance connection from the output to plus 5 if the output is high. So as a consequence, here, let me just jump to the waveforms. To contrast with what we saw last time, you see that the rising and falling edges of the output are equally fast in this case, because in both cases you have a low impedance connection to the appropriate voltage, whether it's plus 5 or ground, depending on which of the two MOSFETs is on, the NMOSFET or the PMOSFET. Okay, now let me show you how I wired this up. So I decided to try to make it look somewhat like the schematic, so I put the PMOSFET on kind of up, and I put the MOSFET down. So here is gate drain source. So both gates go, so this is AWG channel 1. So it goes directly to the PMOSFET's gate, and then there's this little blue wire going over to the NMOSFET's gate. And then the two drains are connected together by this blue wire, and that also serves as my output, which I am looking at with scope channel 2. Meanwhile, scope channel 1, which you can barely see over here, is monitoring AWG1. And then, okay, so for the NMOS, the source is connected to ground with this little black wire. And for the PMOS, the source is connected to +5, which is this blue stripe on the top with this little red wire. Okay, good. And we were looking at the waveforms. And let me just see what the script wants us to look at. Well, we were supposed to try at a very low frequency to see how well it works, but it already works quite well at 20 kilohertz, so maybe I won't go down to 1 kilohertz because it'll continue to work well there. Let's instead go up to higher frequency. So I think this is a frequency where the NMOS with the original 10K resistor was starting to fail. So if we go up another factor of 10, then that's where it was starting to fail with the 1K resistor, I think. So let's go up to 200 kilohertz. Well, actually, we didn't see it fail, but it would have failed if we had looked, if we had gone that high. So, okay, this is still doing quite well at 200 kilohertz. Although I think you could see if we went up another factor of 10, it would struggle. So we can go up to, I guess we could try a megahertz. And let's see, so then we can zoom in a little more. Well, that's kind of hard to see what's happening. Gee. Okay, so actually it really does pretty poorly at a megahertz. Yeah, okay, so it seems like, let's try half a megahertz. That does okay, just barely okay at half a megahertz. And then I guess we already saw 200 kilohertz. That does pretty well there. Okay, so I'd say like a few hundred kilohertz is kind of the limit of how well this thing can do. Let's, where are we? Uh-oh. Okay, yeah. So it seems like a few hundred kilohertz is about as high as this thing can go with these big transistors. So this is like, yeah. But that's still, so I think it does as well both going from low to high and going from high to low as the NMOS did when its output was going from high to low. Because in this case, the output is kind of, you know, like affirmatively pulled either down to ground or up to +5 by one of the two transistors, instead of having to be kind of weakly pulled through the pull-up resistor. So yeah, so it's kind of a strong connection either to ground or a strong connection to +5, depending on which state it's in. And again, only one or the other of these transistors is on at a time. So if we're above threshold, then if the input is high, the NMOS transistor is on, which pulls us down to ground. If the input is low, the PMOS transistor is on, which pulls us up to +5. One more thing I think we could do, which I guess the script doesn't tell us to do, let's try a triangle wave instead of a square wave. Let's also slow it down a little bit. And we can try to look more closely at the transition crossing. So let's go down to, well, what the heck, let's go down to 1 kilohertz. That's kind of something that we were told to do and we didn't do. So we'll go down to, we were told to do. Okay, so, I think we were told to do by me, but we were told to do. Okay, so there it is at 1 kilohertz. Let's change this square to to a triangle. And then let's take a look. Ah, okay. So it seems like here's, you can see the, let's see, this must be the PMOS turning on at this point. And then this must be the NMOS turning on at this point. And I guess I don't really see any place where neither one is on. I guess it kind of, we didn't match these transistors in any particular ways. So, wonder what happens if we zoom in. Yeah, we trigger on channel 2. And if we zoom in a little bit, okay, yeah, I don't see anything weird there. And what if we do falling instead of rising? Yeah, I don't see anything weird there. So you see, we don't see that gate plateau effect. So what does that imply about which one? The fact that we don't see that gate plateau effect, I wonder if that tells us something about, is at least one of them always on? Yeah, I wonder, actually, I have to think it through. Okay, so I'm thinking aloud and I think it's not working. But the fact that we do not see the gate plateau that we saw earlier, I guess we saw the gate plateau in the previous lab, kind of very close to threshold. And I think we also saw the gate plateau a little bit earlier in this lab. So we don't seem to see that here. And I wonder if that tells us something about whether there's a phase of the input going up and down where both transistors are momentarily on. But I don't seem to be able to think that through on my feet aloud, so you can ponder that if you want to. If you come up with a good answer, let me know. Meanwhile, we're going to go on to part 3.3, which is to make a NAND gate. Cool. So we're going to add another pair of MOSFETs. So we'll have 2 PMOSs and 2 NMOSs, and we will make a CMOS NAND gate in just a moment. Okay, here is part 3.3 of lab 21. So this is building a CMOS NAND gate. So we use 2 of these NMOS FETs, 50N06, and we use 2 of these PMOS FETs, 47P06. They have the same pin assignment, gate, drain, source from left to right if you are looking at the print on the package. So let's see how this works. So maybe we should draw out the truth table for a NAND gate. A and B the opposite. So let's say low, low, so false, false. That means AND is false. So NAND is true. Okay, low, high, AND is false. Right, okay, and then high, low, and this should be high. And then high, high should give us low. Okay. So let's see what happens if we have both inputs low. So if A is low, then this NMOSFET is off. So if this NMOSFET is off, then we cannot have a low impedance connection to ground because these two are basically in series. Okay, so then the question is, can we have a low impedance connection of +5? So now, if this is off, then we do have a low impedance connection to +5 because this is on. Okay. So, yeah, if they're both low, you see this is on, this is also on. So we actually have in two places here a low impedance connection to +5. And meanwhile, these are both off. They're in series with each other, so it would be suffice for one to be off, but they're both off. Now, if A is low and B is high, so if A is low, this is off, this is on, so the output has to be high. So if B is high, this will be off, so this is not connecting us to +5, but this one is. So good, so we have high in that case. If this is high and this is low, so A is high, so this is off, but this is on. B is low, so this is off, so there's no connection to ground. But this is on, so there is a connection of +5. Good. So these three are all fine. Now, if they're both high, this is high, so this guy is off. This is on. This is high, so this is on, and this is off. So there's no connection to +5 because these are both off. And there is a connection to ground because these are both on. These both have to be on to get a low impedance connection to ground because they're in series. Either one of these can be on to get a low impedance connection to +5 because they're in parallel. Good. So I think that makes sense. So now let's look at how it is wired up. So it's a little more complicated. So let's see, so I tried once again to try to make the circuit look a bit like the schematic. So this is PMOS, this is PMOS, this is NMOS, this is NMOS. In fact, to be more specific, this is the left-hand PMOS. This is the right-hand PMOS. This is the upper NMOS, and this is the lower NMOS. Okay, and I am driving this using 2 channels of the waveform generator. So here is waveform generator channel 1, and it is going to this gate, the gate of the left-hand PMOS. And that should also be going to the gate of the left-hand NMOS, and it is because this little blue wire makes that connection from gate to gate. Then, this is AWG channel 2. It is going to this gate, which is the right-hand PMOS, and then there should be a connection from there to the right-hand NMOS, and there is. That is this wire from gate to gate. Okay, it's right here. Then, so those are all the gate connections. The output of the circuit is where this right-hand PMOS meets the left-hand NMOS. So, okay, so scope channel 3 is monitoring the drains of those two. Yeah, so it's the drain of this guy, which is connected to the drain of this guy. Okay, so that's scope channel 3. By the way, scope channel 1 is monitoring AWD channel 1, and scope channel 2 is monitoring AWD channel 2 in a way that you can't see. Then, the source of this right-hand PMOS is going up to +5. The source of this left-hand PMOS is going up to +5. That makes sense. Oh, and the drains of these two PMOSs are connected together by a little blue wire back here, okay? And then the source of this NMOS goes to the drain of this NMOS. So that's this little blue wire. Yes, it's going from here over to here. The source of this NMOS is going to ground. That's this little black wire. And I think that's it. Oh, and then, right, so this drain, I think we already saw that. So these drains are connected together by this wire. Okay, so that's all the connections. Now let's test it out. So I decided, right, so instead of using push buttons, I'm using the waveform generator to test it. So I have here 2 channels of waveform generator synchronized. Channel 2 is a kilohertz square wave. Channel 1 is a 500 hertz square wave. They're both going between 0 volts and 5 volts. They're synchronized. And so then scope channel 1, which is yellow, is looking at the input A. Scope channel 2, which is blue, is looking at input B. And scope channel 3, which is magenta, is looking at the output. And so, see, there's a little glitch here. That's kind of interesting. Also, I stopped the scope, so we can run it later. But but you can see low, high, 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 low, high, 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 low, high, high, high. So it's only low if both inputs are high. And then there's a sort of interesting glitch. And let's see why that makes sense. So it seems like when A goes from high to low and B goes from low to high, then there's a kind of just an instant where it seems like we're momentarily connected to ground. Let's see if that makes sense. It seems like to be connected to ground, you have to have A and B both high. So I guess there's an instant where it thinks that channel 2 has gone high, and it doesn't realize yet that channel 1 has gone low. So it's sort of, yeah. So you see a little bit of a glitch. And, I think there's no way to avoid that 100%. Is there? Maybe if you absolutely perfectly fine-tune all the threshold voltages, you can avoid it for the most part. Anyway, that seems like that's the correct truth table. You see this input A is high, high, low, low, high, high, low, low. The other one is high, low, high, low, high, low, high, low. And then the output, yeah. So it's low when the inputs are both high. Otherwise, it's high. Good. And then we can run it, and you still see it running. Yeah, this glitch is a little more prominent now. That's kind of interesting. Actually, the glitch is less prominent now. I kind of stopped and resynchronized. And I might be able to tweak the timing of the two input. I mean, it's kind of cheating, but I might be able to tweak the timing. Let's see, so this says phase 0 degrees. Well, maybe we don't care that much, but here, let me see if I make this phase 1 degree. Let's see what happens. The glitch seems to get more prominent. What if I make this phase -1 degree? Oh, 359 degrees. I think the glitch is mostly gone now. Yeah, so I guess you can cheat a little bit and adjust the timing of A and B turning on and off. Okay. So anyway, cool. We have our homemade CMOS NAND gate built from 2 PMOS and 2 NMOS FETs. All right, so that's our first digital lab. In the next lab, we'll introduce Arduinos.